Welcome to CubeWorks. 3 hours before a distribution main burst in Cebu in 2024, the pressure in that pipe segment had been spiking 18% above normal. It happened every morning, at the same time, for 4 consecutive days. The break cost 4.8 million pesos in repairs and emergency response, forcing an 18-hour road closure and leaving 2,400 customers without water for nearly 2 days. Those warning signs sat in a dataset for 3 hours. The utility simply lacked the dashboard architecture required to see them. Philippine water networks often consist of multi-generational materials sharing the same trench. Asbestos cement from the 1960s sits alongside ductile iron from the 90s and UPVC installed last year. Modern hydraulic loads and rapid population growth place unprecedented stress on this legacy infrastructure. The pipes are old, but the demand patterns are new. This stress manifests as pressure transients, rapid spikes that cause localized forces far exceeding original design limits. Between 40 and 65% of pipe breaks in Philippine utilities occur between 6 and 9 a.m., correlating directly to the simultaneous morning demand surge across the network. Predicting these failures require high-frequency sensors. Most networks currently lack the hardware to collect this data. Shifting from historical design assumptions to real-time physical monitoring is the only way to prevent these catastrophic failures. Pressure monitoring is a standard operational requirement for water utilities in Europe, Australia, and Singapore. The methodologies described here follow Water Research Foundation and IWA best practices, adapted specifically for Philippine infrastructure parameters. Proactive transient management is a standardized engineering science. Normal operating pressure in Philippine systems typically ranges from 20 to 60 meters of head. A pressure transient is a high-speed wave traveling through the network at up to 1,400 meters per second. These waves are triggered by rapid valve closures, pump starts, or the sudden opening of thousands of taps during the morning peak. While healthy pipes absorb these shocks, aged pipes with walls thinned by corrosion will crack under the same force. As this waveform shows, the failure is caused by the transient peak, often 80% above normal operating levels, which lasts only a few seconds. Standard telemetry logging every 15 minutes misses these spikes entirely. High-frequency logging at 1-second intervals maps the true stress on the pipe. Without high-frequency IoT data, utilities remain blind to the forces actively destroying their assets. Digital monitoring depends on physical isolation. This is achieved by dividing the network into pressure zones controlled by pressure-reducing valves, or PRVs. These zones ensure adequate service to hilltop customers while preventing destructive overpressure at lower elevations. In hilly Philippine cities like Cebu or Baguio, multiple isolation zones are an absolute necessity for network stability. An effective IoT deployment at a PRV pulls 3 critical data streams: inlet pressure, outlet pressure, and flow volume. This allows operators to track set point drift, monitor supply adequacy, and calculate the water balance for each district-metered area. Monitoring a single PRV chamber requires roughly 61,000 to 136,000 pesos in hardware. For a district with 15 PRVs, the total hardware investment scales to approximately 2 million pesos. Physical zone isolation via PRVs is the mandatory foundation. Digital intelligence is useless without mechanical control. Sensor placement must be strategic to maximize network intelligence while minimizing capital costs. The first priority is the boundary between high and low elevations, where pressure differentials are most extreme. The second is immediately downstream of pump stations. Third, sensors must protect critical mains serving hospitals and commercial districts. Any pipe segment with a history of frequent bursts should also be monitored to definitively diagnose the cause of failure. Operators should also integrate these new sensors with existing DMA boundary flow meters, which already serve as embedded pressure points. A medium-sized district can achieve high-resolution visibility with 25 to 50 sensors at an installed cost of 30,000 to 60,000 pesos per node. Building a proactive smart grid relies on surgical sensor placement at these points of maximum stress rather than blanket citywide coverage. Once the data is flowing, the utility must define automated alarm rules to drive immediate operator response. Static overpressure alerts allow operators to adjust PRV set points before physical pipe limits are approached. Minimum pressure alerts during peak demand help diagnose whether a supply shortage or a network restriction is causing service drops. Statistical anomaly alerts track standard deviations to uncover developing leaks or failing valves before they trigger a static alarm. Finally, a rapid pressure drop of more than 10 meters within 1 minute provides the definitive signature of a catastrophic main break. This alert enables the control room to instantly identify the affected zone and isolate the failure before major flooding develops. High-frequency data only provides value when it is transformed into automated alerts that outpace the speed of physical flooding. Securing funding for a pressure monitoring network requires a clear executive financial justification. A medium-sized district experiencing 4 main breaks per year loses approximately 4.8 million pesos in direct repair and response costs. Proactive management typically reduces burst frequency by 62%, saving 3 million pesos annually in this scenario. There is also a significant secondary benefit. Reducing excess pressure mechanically lowers the rate of non-revenue water leakage. Reducing pressure in just 2 overpressured zones can recover over 1 million pesos in monthly production costs for a mid-sized utility. This also prevents 228,000 customer hours of supply interruptions annually, drastically improving service reliability metrics. Against a 1.8 million peso investment, a comprehensive pressure monitoring network yields 15.4 million pesos in annual savings and recovered water. With a payback period under 2 months, an IoT pressure monitoring network acts as an immediate revenue recovery engine for the utility. That 4.8 million peso disaster in Cebu was preceded by a 3-hour warning that was missed because the utility lacked the sensors to see it. Your own network is broadcasting these exact same invisible stress signals right now. Identify the 5 highest-risk pipe segments in your network today. Those 5 locations are your first priority for pressure monitoring. Next week, we compare SCADA versus IoT architectures to determine which upgrade path makes the most sense for modern water utilities. Utility failures are predictable if you gather the correct physical intelligence.